In the previous lecture, we have discussed in detail the London equations and the penetration depth. In other words, you can say we have discussed the electrodynamics of superconductors. But our discussion was limited to the fields which do not vary alternately with time. But we have considered the DC field. When you say DC field, that field may be either time independent, but it may be time dependent, but it does not vary with time in sinusoidal manner or alternating manner. Okay. So our discussion on the superconductivity was actually at very low frequency, or you can say at zero frequency. Now the same problem we are going to discuss at high frequencies. It means in this case we will consider the fields and the currents involving in our calculations are actually of alternating nature, or you can say that they are AC. We are going to discuss the problem in case of AC field. Okay, but we will need the results which we have obtained in our previous lecture. So I have noted here the important results which will be desired to discuss the present problem. You can remember that one of the most important result, which is actually called the London first equation, we have derived in this way. This was dJs by dt equal to ns times E square over m times E. Here actually you know this Js is actually the super current density and ns represents the super electron density. It means it is number of super electrons per unit volume. Okay. M is mass of the electron and E is the electric field, and a small e represents the charge of electron. Okay. And then we have obtained the expression for the penetration depth, which is also called London penetration depth, and it is denoted by the symbol lambda d. And we have obtained that this lambda d square is equal to m over mu naught times ns times E square. Okay. This was the expression which we have already derived in our previous lecture. Okay. And so from here you can see, if you see that in equation A there is a factor ns times E square over m. So let us find the value of this factor ns E square over m from this result, and that will be equal to 1 over mu naught times lambda d square. So this equation A, by the use of this equation B, you can write in this manner. This is dJs by dt equal to E over mu naught times lambda d square. You know this mu naught is the permeability of free space. Okay. These were the important results which we have obtained in our first part of the lecture on the London equation and penetration depth. Actually, in this present lecture, our aim is to discuss the again the penetration depth. Okay. And we will also learn about another depth which is called skin depth. If you have watched my video on skin depth in the playlist of classical electrodynamics and electromagnetic theory of my channel, you can see the detailed discussion of skin depth in case of propagation of electromagnetic wave in a conducting medium. So we will also see how this penetration depth lambda d, which is called London penetration depth, and the skin depth, which will be represented by the symbol delta, are related together. Okay. So now let us consider that the current and the field we are assuming is sinusoidally varying with time, because as I have told you, in present case we are going to discuss the superconductivity at high frequency, And if you consider the field and current are of alternating nature or sinusoidal nature, then they will be of high frequency. So if the current is of sinusoidal nature, the best representation of this supercurrent density may be written like this. This is J naught times e to the power iota omega t. Okay, here omega is the frequency of this current. Okay, and the magnetic field intensity H is given as H naught times exponential iota omega t. Here the frequency of the current and the field are same, which is equal to omega. Okay, and so from this equation 1 you can see, if you find the time derivative of this Js, that is dJs by dt, what will be this? This will be iota omega times J naught times e to the power iota omega t. But you can see equation 1, this J naught times e to the power I omega t, this is simply Js. So this can be written as I omega times Js. Okay. Now see, d dt Js is equal to I omega Js. The function Js is in both sides. So from this result you can see that this operator I omega is at the place of the time derivative operator d dt. So we can see that this operator d dt is just equivalent to I omega. Remember, omega is the frequency which is a physical quantity, but I omega is not a physical quantity, it is an operator, and this operator is just equivalent to this time derivative operator. Okay. But you have seen here that this dJs by dt is equal to this much. So at the place of this dJs by dt, you can put E over mu naught lambda L square, and that will be equal to iota omega Js. Okay, and so from here this Js is equal to E over I omega mu naught times lambda L square. But you know that this 1 over iota is equal to minus iota. Okay, so this result is written as minus iota E over mu naught omega lambda L square. Okay, this is the expression for the supercurrent density Js. Now you know the electric displacement vector D. You have definitely studied about this electric displacement vector in your course on electrostatics or in course of physics of dielectrics. If you have not studied it, I will suggest you, there is a playlist of the name Physics of Dielectrics in my channel. You can watch there in very detail the concept of this electric displacement vector D. This is actually an auxiliary field vector for the electric field vector E. As we have considered that all the fields and all the currents are sinusoidally varying, so we can also express this electric displacement vector in this manner. This can be written as d naught times exponential iota omega t. And so from here, when you will differentiate it with respect to time, then you will again get like this. This will be iota omega d. Okay, so this is d by dt equal to iota omega d. Okay, now actually from here you can see that this d dt dd by dt is equal to I omega epsilon naught E. Why? You know, this displacement vector D is related to the electric field vector by this relation. D is equal to epsilon naught E if you neglect the polarization. If you will take under account the polarization, then D is equal to epsilon naught E plus P. But here there is no polarization, so D is equal to epsilon naught times E. Here epsilon naught, you know, this is the permittivity of free space. Okay. Now, after getting these results, we can apply the Maxwell's fourth equation, and we will use all these results in that Maxwell's fourth equation. You know, Maxwell's fourth equation is curl of H is equal to J plus d by dt. Actually, here the partial operator has been not used. Instead of that, we have used actually the ordinary differentiation, because we are considering that this d vector or j vector or e vector all are only function of time, not of position. So we have considered like this, okay? And this J is the total current density. But you know, in case of superconductor, there are two types of conducting electrons. One is called normal conducting electrons, and another is called superconducting electrons. Okay. So this J can be expressed as the vector sum of the current density due to the normal conduction current, conduction electron, and due to the super electron. Okay. So J is written as Jn plus Js. Okay. And so curl of H is equal to Jn plus Js plus dd by dt. Okay. Now you know that this Jn, which is actually the normal current density, according to Ohm's law, microscopic form of Ohm's law or vector form of Ohm's law, you can write this sigma n into E instead of Jn. This is just Ohm's law. J is equal to sigma E. This is the vector form or microscopic form of Ohm's law. Here this sigma n is the electrical conductivity of our material due to the normal electron. Okay, and E is the electric field. And Js you have just obtained here. You can see the equation number 2. Js is equal to this much. So instead of Js, now you can write this much. This is minus iota E over mu naught omega lambda L square. Okay. And time derivative of displacement vector, you can see equation 3. This is equal to this much. So we have made the use of all the above results in this Maxwell's equation. Okay. Now you can see the electric field vector is present in all the three terms in RHS, so you can take it as a common factor, and therefore curl of H is equal to this much. You can see. Okay. Now actually to get the desired result, we will take the curl of this equation 4, or you can say that we are going to taking curl of both sides of equation 4. Okay. So when you will take curl of LHS, what will be that? That will be del cross H. Del cross means curl. Okay. And in RHS, this is actually a scalar factor, so it is outside of the operator, and this will be curl of E. Okay. Now from the triple product of vector product, from the definition of triple vector product, you can express this LHS in this manner. This is del dot H del minus del dot del H. Okay. And RHS has been taken at H. Okay. But as you know from the Maxwell's second equation, this is del dot H equal to 0. This is nothing. This is Maxwell's second equation. And the Maxwell's third equation says that curl of E, that is del cross E, this is equal to minus dB by dt. But you know B, which is magnetic induction or magnetic flux density, this is equal to mu naught times H. So when B will be replaced by mu naught times H, then curl of E is equal to minus mu naught times dH by dt. Okay. But you know the operator d dt is equivalent to I omega. So writing I omega instead of the operator d dt, our result is curl of E equal to minus iota omega mu naught H. Okay. Now this all these results, that is at the place of this del dot H we will put 0, okay, and at the place of curl of E we will put this much in this result. So when you will substitute this, you will get that this is this del dot del is del square, which is called Laplacian operator. So this is minus Laplacian H equal to this much times this much. This is at the place of curl of E, okay. And so you can see minus sign is present in both LHS and RHS, so that will cancel out. And now except the factor H, the remaining factor, by the remaining factor I omega mu naught, we will multiply the terms inside this first square bracket. So after multiplication you will get del square H equal to 1 over lambda L square minus mu omega square mu naught epsilon naught, okay, and plus I omega mu naught sigma n, okay. Actually this is the very important result which we have obtained in case of the alternately varying electric field and magnetic field and the electric displacement vector, okay. Now actually in this result, what the different terms in RHS represents, now you can see the term H over lambda L square. See here, the first term, this is H over lambda, H is common. So H over lambda L square, actually this represents the field penetration due to supercurrent. It means how much the magnetic field will penetrate into the surface of the material, that is represented by this term. Because you have learnt in your previous part of the lecture on London equation that d2js by dt square is equal to js over lambda L square. Actually this is just analogous to this, okay. This result is quite similar to this. Instead of this d square dt square operator, you can see there is del square H operator, okay. So this term H over lambda L square represents what? This represents the field penetration due to the supercurrent, okay. Now the next term, which is minus omega square mu naught epsilon naught times H, this term actually represents the field penetration due to the displacement current, okay. How much electric field is penetrated into the surface of the material due to the displacement current, this term represents that very fact, okay. So penetration is not only due to the supercurrent, but it is also due to the displacement current, mark it, okay. And this is actually this third term, which is omega mu naught sigma n H. This also represents penetration of the field, that is the magnetic field, due to the eddy current. So actually the penetration of magnetic field in the surface of the material is due to three regions. First of all, you have seen that penetration of magnetic field is due to the supercurrent. Then you can see the penetration of magnetic field into the surface is due to the displacement current, and finally you see that penetration of magnetic field into the surface of the superconductor also takes place due to eddy current. Because whenever a conductor is placed in a varying magnetic field, you know an eddy current is produced, and that eddy current or disturbing current is also responsible for the penetration of magnetic field. So this result, these results are actually very different from the case of DC field. In case of AC field, you can see that in the surface of a superconductor in a magnetic field, there will be a penetration of magnetic field inside the material due to three reasons. These are due to the supercurrent, another penetration is due to the displacement current, and the third penetration is due to the eddy current. Okay. Now you can check that these results are correct or not, because you have already studied these things in case of DC field. So when you will apply this result in case of DC field, what will be our result, we can see. If you are talking about the DC fields, you know these two terms will vanish. This will be 0 and this will be 0. Why? Because these two terms contains omega, and you know in case of DC field, omega is equal to 0. So in case of DC field, there will be no penetration of magnetic field due to the displacement current and due to the eddy current. There will be only one penetration due to the supercurrent, and that is the case of DC field, which we have already learnt in our previous lecture. Okay, so you can see in this condition, this equation which you have obtained here, this equation now becomes like this: del square H equal to H over lambda L square. Okay, so actually this result is just you can see this will be 0, this will be 0 in case of DC field. So our result is del square H equal to H over lambda L square. And if you can remember your previous our previous lecture on London equation, you can see this result was same as predicted by London. So our theory for the high frequency superconductivity is correct, because when we apply the condition that our field is not sinusoidally varying, its frequency is 0, it is a DC field, then this result which we have obtained in case of alternately varying field just becomes the result which we have seen in our previous lecture in case of the DC field. Okay. Now, if you are talking about the microwave frequencies, then the frequency omega will be sufficiently high and the corresponding wavelength lambda will be small, because you know speed of the microwave will be c, and c is equal to f times lambda. So if f is large, lambda will be small, only then c will remain constant. So now in case of microwave frequencies, if we consider the microwave frequencies, it means we are considering the case of a high frequency and a smaller wavelength. In that condition, what will be this factor? You can see this omega square mu naught epsilon naught. We are talking about this factor. Actually, you know, the speed of the any electromagnetic wave in free space, c, is equal to 1 over a square root of mu naught epsilon naught. Okay, so mu naught epsilon naught will be simply 1 over c square. So this is equal to omega square over c square. But you know, omega is equal to 2 pi f, where f is the frequency, omega is cyclic frequency, and so this result can be written as 4 pi square f square over c square. Okay, but lambda is equal to c by f. So when you will replace this f by c by 1 by lambda, your result will be omega square mu naught epsilon naught equal to 4 pi square over lambda square. So now at the place of this factor, omega square mu naught epsilon naught, which is present here, we can write 4 pi square lambda by lambda square, and then that equation becomes del square h equal to 1 over lambda L square minus 4 pi square by lambda square plus I omega mu naught sigma n times h. Okay. Now it is obvious from this result that penetration depth lambda L varies from 300 angstrom to 5000 angstrom. Actually, this is the experimental fact. This is the idea which has been obtained actually from experiment. Okay, so the term due to the eddy current will predominate. That will be dominating term because this lambda is large, and in this case so the term 1 over lambda square will be actually very small, and we can neglect it, and this term will dominate over the term due to containing that due to the term containing lambda. Okay. In other words, you can say that it is sigma n which determines the properties of superconductor in this range of frequencies. That is, the normal electrical conductivity will be actually the conductivity of the material. And so in this condition, the superconductor behaves just like a normal conductor. Okay. And so you can see that in this range of frequency, this depends on the number of normal conduction electron that is quite large at high frequency. Okay. Now actually we will see what is the relation between the penetration depth and the skin depth, which is denoted by the symbol delta. Actually, as you have seen earlier that this Js is equal to this much. You have already seen this. Okay. And Jn, you know from Ohm's law, this is sigma n times E. So when you will find Jn by Js, you know we cannot find the ratio of two vectors because division is not defined in a vector. So we have taken here modulus. And when you will take the mod of Jn and Js and you will find this ratio, your result will be this much. This is mu naught omega sigma n lambda L square. Now actually this skin depth and the penetration depth are related by this relation. Lambda L over lambda L square over delta square. This is equal to 1 over 2 Jn by Js. Remember it. But Jn by Js, this is equal to this much. So if you will substitute this value here, you can see you have a result will be lambda L square over delta square is equal to this much. This is mu naught omega sigma n lambda L square over 2. And so from here you can see that this lambda L square will cancel in both sides, and delta square is equal to this much, and so delta is this. This is actually the expression for the skin depth. Now you can see that if we are talking about the very large frequency, omega is very high. If omega is very high, it is clear from this result that delta will be very small. Okay, delta is inversely proportional to a square root of omega. So for the sufficiently larger value of omega, this skin depth will be very small. Okay, and if it is very small, definitely this London penetration depth will be greater than delta. Okay, and if the lambda L is greater than delta, then definitely this Jn will be greater than Js. What does it mean? It means the current density due to the normal electron will be greater than the current density due to the super electron. So in this condition, you can conclude that our superconductor behaves just like a normal conductor. So if you are talking about a very high frequency, In case of very high frequency, a superconductor behaves like a normal conductor. Okay, this is a very remarkable fact. Okay, so this implies that at high frequencies, superconductors behaves like a normal conductor. This is a very important fact, and you should remember it for objective questions. In your examination, if objective question is asked, can a superconductor behave like a normal conductor? The answer will be yes. But when frequency is very high. Okay. So this is all about the superconductivity at very high frequency, and I hope you have definitely understand the each and every step of our calculation and the concept. Okay. Thank you very much.